Welcome to Allen High School's APIB HL1 discussion about acids and bases. Now, in this next question, we are given three different systems with the corresponding Kas. These are all weak, all equilibrium systems. Now, the question asks us to identify the conjugate pair. What that means is the acid with its conjugate base that is best for preparing a buffer of pH 7.2. Now, there's two parts to this. We have to identify and then explain our choice. Now, when picking a buffer, our goal is to have a pKa as close to the pH at which we desire to buffer as possible. May not be able to lean dead on, but we want to get as close as possible. Now, this is in part B, a non-calculator situation, so I am going to approach this as if you cannot use a calculator. Let's take a look at the first one. If we were to predict the first one, this isn't a 1 in front, so what we're going to do is look at that power, go down by 1, so that pKa is 6 point something. This next one, that's not a 1. If it's a 1, it would have been easy because then it would have just been 8. Fortunately, it's not, but it's 7 point something. All we have to do is subtract 1. And then this last one, the pKa, let me erase that and get it out of my way. The pKa is going to be 1 point something, which is way out of bounds. Okay, nowhere near what we want to be. And so I'm going to eliminate this one and this one because my best choice is this center one because the pKa is closest to the pH at which I want to buffer. So that's your answer. Your identify is this. That's probably worth a point right there. And its conjugate partner is HPO4 2-. And the reason is because the pKa is closest to 7.2. Okay? Actually, if you did that calculation, it is 7.2. So if you had a calculator, all you had to do is take minus the log of this number, and you would find it is right at 7.2, which makes the next parts a little easier. Now, let's go to part B. It asks us, how would we prepare that buffer? So I have H2PO4-, that's an ion. And I have HPO4 2-, that is also an ion, an anion. And I want to get them in there is a 1-to-1 mole ratio. And so I want to add somehow equal numbers. So I want the moles of this H2PO4- to equal my moles of HPO4 2-. Now, I can't just add, whoa, that was kind of fun. I can't just add a anion. I have to have a salt. So you need to add some sort of a salt of each of these. So I would say, to be as precise as possible, equimolar amounts of, pick a cation, something simple, sodium or potassium, sodium dihydrogen phosphate and sodium hydrogen phosphate. Now, if you had picked the wrong answer in A, as long as your answer to B was consistent, you're good to go. All right, let's go on to C. What if I doubled the concentrations? How is this going to impact my pH? And additionally, there's a question about capacity. How is the capacity affected? So let's address the first issue. If we have our Ka equal to, and you can do this via Henderson-Hasselbach, is also a great argument for this, PO4 2- over H2PO4-. Now, what it's saying is I multiplied this by 2 and I multiplied this by 2. Well, it's not going to do anything to the Ka. You're still going to get those two very close to cancel, at least be the same as they were before. And your Ka will equal to your H plus. So you could go on to say Ka still equal or approximately equal to H plus. So pH is not changed. This is where I think that Henderson-Hasselbach is a little easier to see, because if we did pH equal to pKa plus the log of those conjugate base over my acid, dihydrogen phosphate ion, okay? Well, if I multiplied that by 2 and I multiplied that by 2, the 2's cancel and I still get the same pH. So the answer to part 1 is there is no change in pH. Now, what about the buffer capacity? Well, the answer to the second part is if you increase the molarities of your weak acid and your conjugate base, you increase the amount of acid and base that can be added before the pH changes. Which is, you know, before it changes significantly. It'll always change a teeny bit, but we're talking about significantly. That's what buffer capacity is. The goal of a buffer is to not change pH. Buffer capacity is the amount it can suck up in terms of acid and base before changing pH. So the key part of this answer is that you increase your buffer capacity when you increase molarity. That's your therefore. I ran out of space there, but I think you get the idea. Let's go on to the last point. What do we do? Oh my gosh, we don't have the solid salt of both of them. All right. So let's say we have, and it said either one, so we can pick. I'm going to pick this way. All we have is this. We don't have the salt of this. So I have to find a way to form some of this. Now, if you go back in your notes, you'll see that we addressed that. Let's throw off that boring old sodium ion. Now, I want to somehow convert part of this, and remember an ideal buffer is close to 50-50, right? So I have an acid. If I want to react the acid, I'm going to add to it a strong base. Now, I don't want to dilute all, or I don't want to, neutralize all of this. I want to neutralize half of it, all right? So for every 1 mole of this, I want to add half a mole of my hydroxide. Remember, let's do a start, a shift, a stop. So that's a 0. This is a stoichiometry, because an acid plus a base, regardless of strength, is a stoichiometry till one of them runs out. That was a lot to say. So it's 1-to-1. Isn't that lovely? Not all of those different squared and cubes and all of that. Minus 0.5 plus 0.5. And showing this would really prove to the person reading your paper that you haven't just memorized, that you understand. Because that's always our goal. Now, by doing that, you have a 50-50 mixture. Now, honestly, another way you can do this is you can titrate that initial one and use a pH probe to measure pH, and that would be what a lot of people would do anymore. Okay, depended on how precise it had to be. So if you titrated that H2PO4 minus with your base, maybe it's sodium hydroxide or potassium hydroxide or lithium hydroxide, it doesn't really matter, okay? Titrate with hydroxide, use a pH probe until the pH of the system was equivalent to 7.2. Okay? So that would be an alternative way to do that. All right, I have one more I want to do for you. There's actually a few more in your notes that if you work or come in, I will help you work, and I will certainly show you the answers to those as needed. But I am going to do one more. So until that last video of our series, this is signing off.